After studying this module, you shall be able to know about the role of statistics in fingerprint analysis, learn about the various modes of fingerprint individuality. This module examines the underlying statistical basis for fingerprint comparison and reviews the effort that has been made to measure friction ridges variability as it relates to forensic comparison and identification of fingerprints. These well-developed areas of study do contribute essential information that establishes the feasibility and utility of fingerprint identifications, but they do not provide criteria for concluding that two fingerprints were made by the same finger. Neither does the long-standing practice and effectiveness of fingerprint evidence provide such criteria. This module is specifically considered with the question how much correspondence between two fingerprints is sufficient to conclude that they were both made by the same finger. The amount of correspondence has two dimensions: quantity and quality. Quantity itself includes two aspects. The first is how much of the skin surface is represented in the comparison, and the second is how many and what kind of details make up the correspondence. The dimension of quality in a fingerprint correspondence is determined by how clearly and accurately the skin surface is represented in the two prints. An adequate answer to the question posed is not currently available. The best answer at present to the question how much is enough is that this is up to the individual expert fingerprint examiner to determine based on that examiner's training, skill and experience. Thus, we have an ill-defined, flexible and explicable selective creation for establishing a fingerprint identification. The need for a standard objective citation has itself been controversial because subjective methods have been so universally effective and accepted for so long. Even admitting the need, there is considerable difficulty in defining meaningful measurements for quality and quantity in fingerprints comparison. This difficulty will become apparent in this review of the efforts that has been made. Now, the standards in fingerprint identification. Any unbiased, intelligent assessment of fingerprint identification practices today reveals that there are in reality no standards, that is, the amount of correspondence in friction ridges detail that is necessary for a conclusion of identity has not been established. There is an even more basic deficiency, however, is capable of measuring the amount of correspondence in a fingerprint comparison, and there is a third corollary deficiency. There is no methodology in place that is capable of measuring the amount of detail that is available in a fingerprint for comparison to another. In summary, one cannot measure the amount of details in a single fingerprint that is available to compare. Second, measure the amount of detail in correspondence between two fingerprints. Third, objectively interpret the meaning of a given correspondence between two fingerprints. AFIS technology, while holding promise in this area, has been and remains restricted to the task of screening millions of prints and efficiency selecting candidates for fingerprint comparison. Although this is an important, effective and indeed revolutionary task, the comparison itself is reversed for the individual fingerprint examiner. The examiner applies personal subjective criteria that, despite all his historical precedents, legal acceptance and public confidence, are both verge and flexible. Although not directly the subject of this chapter, the above deficiencies are compounded by the fact that neither the education of fingerprint examiners nor the processes of fingerprint comparison is standardized. Furthermore, there have been no objective studies providing validation of the subjective processes that are in place. Recognition of the above deficiencies does not mean that the fingerprint practices are discredited, that they have no foundational basis, or that the process is necessarily unreliable. Given the Daubert criteria, however, the question of reliability is a reasonable one to ask. Legal scrutiny of fingerprint is, after more than 80 years of uncritical public and judicial acceptance, entirely appropriate. Fingerprint individuality models. Soon after the recognition of the value of fingerprints of personal identification, the degree of individuality present in a fingerprint pattern became of interest. Attempts to provide a probabilistic estimate of fingerprint individuality began with Galton's investigation in 1892 and continue to the present day. There have been 10 distinct approaches, including those of first Galton, second Henry Belzgaard, third Roxburgh, ME, Towering, sixth Kingston, seventh Ostelberg, eighth Stoney and Thornton, ninth Campoid, 10th Megar, Bultwell and Zigzig. Some of the models are explained further. Now, the Galton Method, 1892. Galton made the first attempt to quantify fingerprint individuality. His approach was to divide the fingerprint into small regions such that the ridge details within each region could be treated as an independent variable. Galton worked with the photographic enlargement of fingerprints. The enlargements were placed on the floor and paper squares of various sizes were allowed fall haphazardly on enlarged fingerprint. Galton then attempted to reconstruct the ridge detail that was masked by the paper square given the surrounding ridges. He sought the size of square regions where he could successfully predict the actual ridge detail with the frequency of 1 by 2. Galton found that for a square region, 6 ridge individuals on his side, he was able to correctly predict the hidden details with the frequency of 1 by 3, and consequently concluded that a square region with 5 ridges interval on his side was very nearly the size he was seeking. To ensure that any errors would overestimate the chance of fingerprint duplication, Galton used a 6 ridge interval square region and then assumed a probability of 1 by 2 for finding the existing minute configuration, giving the surrounding ridges. The total area of complete fingerprint was estimated to consist of 24 such square regions. Assuming independence among these regions, Galton calculated the probability of a specific fingerprint configuration giving the surrounding ridges P C by R using equation P into C by R is equal to half into 24 is equal to 5.96 into 10 to the power minus 8. Galton next estimated the chance that a particular configuration of surrounding ridge would occur. Two factors were considered. First, the occurrence of the general fingerprint pattern type. Second, the occurrence of the correct number of ridges entering and exiting each of the 24 regions. Galton estimated the probability for coincidence of pattern type, termed factor B by Galton, as 1 by 16, and the probability that the correct number of ridges would enter and exit each region, termed factor C by Galton, as 1 by 256. The latter estimated was largely arbitrary and both were presented by Galton as glossary overestimating the true probabilities. Combining the frequencies of finding the necessary ridge pattern outside the 6 ridge interval regions with the frequency of finding all necessary ridge details within the region, Galton then predicted the probability of finding any given fingerprint P bracket F into P using equation P into Fp is equal to 1 by 16 into 1 by 256 into 1 by 2 into 24 is equal to 1.45 into 10 to the power minus 11. Assuming a world population of approximately 16 billion human fingers, Galton concluded that given any particular finger, the odds of finding another finger that showed the same ridge detail would be approximately 1 in 4, means 1 by 4. Henry Belzard Model. The Henry Belzard approach is used in 6 closely related, fairly simplistic models for fingerprint individuality. Each employs a fixed probability P for the occurrence of one minuta. Assuming independence of these occurrences, the model calculates the probability of a particular configuration of n minute using equation P into C is equal to P into n. Henry was the first to use this approach in 1900 and Bilsgaard in 1911 made the most extensive analysis. Minor variations are encountered in the work of Bose, Wentworth and Welder, Cumins and mildew and Gupta. Now, Henry Model 1900. Henry chose an arbitrary probability of 1/4 for the occurrence of each minuta as well as for the general pattern type and the core to delta ridge count. To use his method, one counts the number of minuta. If the pattern type is discernible, one adds two minuta equivalents. This value is used as n with 1/4 as p. Now, Belzard Model 1911. Belzard's method is particularly important because it is the historical basis for widely accepted rules regarding fingerprint individuality. Bilsgaard assumed that for each minuta there were 4 possible events. First, fork directed to the right. Second, fork directed to the left. Third, ending ridge directed to the right. Fourth, ending ridge directed to the left. Assigning an equal probability for each of these events, Bilsgaard took p as 1/4 and n as the number of minuta. He concluded that to observe n coincidentally corresponding minuta, it would be necessary to examine 4n fingerprints. Belzard went on to calculate the number of minuta needed for conclusive identification. His criterion was that there should be an exception of 1 or less for the occurrence of the minuta configuration in the suspect population. Assuming a world population of 15 billion human fingers, 17 corresponding minuta would be needed. Under his model, 17 corresponding minuta would be found with a frequency of only about 1 in 17 billions. Belzard considered a lesser number of corresponding minuta, for example 11 or 12, to be sufficient for an unequivocal identification if one could be certain that the fingerprint donor was restricted to a particular geographical area, example North America, California. Bose Model 1917. Bose also assumed a value of 1/4 for p but arrived at this value using a different relational. He reasoned that there were at least 4 possibilities at each square ridge interval location in a fingerprint. These were first dot, second fork, third ending ridge, fourth continuous ridge. Now, Wentworth and Welder Model 1918. Wentworth and Wentworth felt that Belzard's value of 1/4 for p was absurdly high and proposed a value of 1/50 for p. This was an intuitive estimate of the value with no further justification or explanation. Now, cumins and mildew model 1943. Cumins and mildew adopted the value of 1/50 that was suggested by Wentworth and Welder, but they also introduced a pattern factor to account for the variation in the overall fingerprint pattern. Cumins and mildew estimated that the most common fingerprint pattern occurred with a probability of 1/31. The estimate was for an Erlang loop and included core to delta ridge count gives cumins and mildew calculation for n corresponding minute and a corresponding pattern. P into C is equal to 1/31 into 1/50 into n. Now, Gupta Model 1968. Gupta conducted a survey of minute to estimate his value for p. He first selected particular minute type and position. He then searched 1000 fingerprints with unknown loop patterns for a corresponding minute in the chosen position. This resulted in a prediction of the frequency of encountering the particular minuta type in the particular minuta position. Gupta found that forks and ending ridges were encountered with a frequency of about 8/100 and that the remaining variety of minuta types were encountered with an average frequency of about 1/100. He therefore chose a value of p is equal to 1/10 for forks and ending ridges and assigned a value of p is equal to 1/100 for the less common minuta types, example dots, hooks and enclosures. A pattern factor of 1/10 and a factor for corresponding in ridge counting 1/10 were also applied. Now, Roxburgh Model 1933. The Roxburgh Model had until 1985 been totally ignored by the forensic science community. Roxburgh based his model on a polar coordinate system. A configuration of concentric circles spaced one ridge interval apart is taken to represent the ridge flow of the fingerprint. An axis is drawn extending upward from the origin and is rotated clockwise. As the angle from the initial position increases, minuta are encountered for each minuta. The ridge count for the original is noted along with the type of minuta. The type of minuta allowed by Roxburgh are identical to Belzard's. A minuta may be either a fork or an ending ridge and may be oriented in one of two opposite directions. Rotation of Roxburgh axis results in an ordered list of minuta types and ridge counts from the origin. Roxburgh decided simply to order the minuta rather than use an angular measure because by doing so he could avoid determination of how precisely minuta position could be resolved along each of the ridges. After defining the system for minuta coding, Roxburgh calculated the total variability which could occur under the model. He initially assumed that the ridge count and minuta types were independent and that the possibilities for each were equally likely. Assuming n minuta are concentric ridges and t minuta types, the number of possible combinations for ordered data is given by equation. Number of combinations is equal to RT into n. An additional pattern factor P was introduced as an estimate for the probability of encountering the particular fingerprint pattern and core type. The total variability was calculated using equation with the following values for the parameters. P is equal to 1000, N is equal to 35, R is equal to 10 and T is equal to 4. Number of combinations is equal to P into R into T into N is equal to 103 into 10 into 4 into N is equal to 1.18 into 1059. The value of 35 for N was used because it has been Galton's estimate for the numbers of minute in a fingerprint, and the value of 4 for T was used because of the 4 options of minuta types. Roxburgh estimated P using Galton's fingerprint classification system where there are 1024 different classification types. R was taken as a conservation value. There are many more than 10 semicircular ridges in a complete fingerprint pattern. The result of equation was therefore presented as a conservation upper bound for the total number of possible fingerprint types under the model. Roxburgh next considered the equation of correlation for successive ridge counts and successive minuta types. Using 271 fingerprints, he recorded the first 4 minuta in each print. The data were classified by the sequence of ridge number and the minuta types. Without statistical analysis, Roxburgh noted that there appeared to be a roughly even distribution with respect to ridge number sequence and also with respect to the number of forks and ending ridges with each ridge count. He did observe, however, an excess of those minuta that cause production of ridges compared to those that cause loss of ridges. Roxburgh attributed this to the clockwise rotation of his axis and a general tendency for ridges to diverge as one proceeds from the vertical. The largest group of fingerprints showing the same sequence of minuta types had 8 numbers. Roxburgh therefore used the value of 271 by 8 as a conservative estimate of the variability of 4 minuta with respect to type. For 1 minuta, the value would be the fourth root of this, or 2.412. Roxburgh proposed this corrected value of t to adjust for the observed correlation. Up to this point, only ideal fingerprints has been considered. Roxburgh further modified his model to allow for poorly defined or poorly recorded prints. Poor recording of fingerprints may cause a true fork to appear as an ending ridge either above or below the ridge bearing the fork. Similarly, a true ending ridge may appear as a fork joining either the ridge above or the ridge below. It should also be recognized that, quite apart from recording difficulties, the nature of some minuta may be uncertain on the skin surface itself. The term connective ambiguity is used here to describe the general phenomena in which one is uncertain of the minuta type. In the extreme, connective ambiguity allows 2 additional configurations for each minuta. There is not only opportunity for change in minuta type, but for a change in ridge count as well. Roxburgh suggested the use of a factor Q for quality to assess the impact of connective ambiguity. The value of Q varies depending on the quality of the fingerprint. It ranges from 1 in an ideal print to 3 in a print where complete connective ambiguity must be acknowledged. 3 is used as the limit because there are 3 possibilities for minuta type and ridge count when complete connective ambiguity is acknowledged. Roxburgh estimated Q as 1.5 for a good average print, 2.0 for a poor average print, and 3 for a poor print. The factor Q decreases the number of distinguishable minuta configuration, contributing a factor of 1 by Q for each minuta. Number of configuration is equal to P into RT upon Q into N. Roxburgh made one additional correlation to account for circumstances where the fingerprint pattern is insufficiently clear to allow proper determination of the ridge count from the core. The relative position of the minuta are not affected, but there is some uncertainty regarding the position of the whole configuration relative to the core. A factor C was introduced, defined as the number of possible positions for the configuration. The pattern factor P was divided by C to correct for this uncertainty. In the extreme, where the pattern is not at all apparent, the factor P must be dropped altogether. Roxburgh's final equation for the number of possible minuta configuration is equation number of configurations is equal to P by C into RT upon Q into N. For a good average fingerprint showing the pattern type and 35 minuta, Roxburgh defines his variable as T is equal to 2.412, R is equal to 10, N is equal to 35, P is equal to 1000, Q is equal to 1.5 and C is equal to 1. Assuming each configuration is equally likely gives the chance of duplication of a particular configuration of 35 minuta. P duplication N is equal to 35 is equal to 1 by 1.67 into 1045 is equal to 5.98 into 10 to the power minus 46. For any particular case, Roxburgh recommended estimating the number of individuals who could have had an access to the location where the fingerprint was found, be it the entire population of a country, city or whatsoever. The chance of duplication of a particular configuration of minuta in this population may then be considered and the number of minute necessary for any desired confidence level may be determined. Roxburgh suggested that a chance of duplication of 1 in 50,000 would be appropriate confidence level for an identification and presented a table with the number of corresponding minute needed for various population and fingerprint qualities. Next, Towering Model 1963. Towering estimated the chance of coincidental fingerprint association in connection with a proposed automatic identification system. The system is based on prior selection of reference minuta on a finger and the recording of a number of test minuta. Relative coordinates derived from the reference minuta are used to describe the position of the test minute. As proposed, the test minuta appear within the triangular region described by the reference minuta and the approximate position of the reference minuta on the finger are known. Towering made the following assumptions. Minute are disturbed randomly. Next, there are 2 minuta types, forks and ending ridges. Next, the 2 minuta types are equally likely to occur. Next, the 2 possible orientation of minuta are equally likely to occur. Next, minuta type, orientation and position are independent variables. Next, for repeated registration of one individual's finger, the uncertainty in the position of the test minuta relative to the reference minuta does not exceed 1.5 ridge intervals. Under these assumptions, the correspondence of the test minuta requires its presence within a circular region of radius 1.5 ridge interval. Area is equal to 7.07 square ridge intervals. The chance of minuta appearing in this region is equal to the minuta density multiplied by the area. The minuta may be one of 2 equally like types and has one of 2 equally likely orientations. The probability of a corresponding test minuta given acceptable reference minuta P into Tm by Rm is therefore given by equation. P into Tm by Rm is equal to 0.707 by 4s is equal to 0.07s. If the chance of encountering an acceptable set of reference minuta on one finger is R, then each person has a 10 into R probability that the reference minuta will be present on one of their 10 fingers. If the number of test minuta is n, then the chance of random correspondence of any one of the individual fingers with a previously defined fingerprint is given by equation. Based on his observation of 20 fingerprints, Turing found a maximum value of 0.11 for minuta density. He also estimated that the probability of correspondence of 3 randomly corresponding reference minuta could be conservatively taken as 1 by 100. Pn corresponding individual is equal to 0.1944 upon 10. Now, Kingston Method 1964. Kingston 20 divided his model for fingerprint individuality into 3 probability calculations in much the same fashion as ME. He first calculated the probability of finding the observed number of minuta in a fingerprint of the observed size. Next, he calculated the probability that the particular minute positions would be observed. And finally, he calculated the probability that minute of the observed type would occupy the positions. Now, summary. The recognition of the value of fingerprints for personal identification, the degree of individuality present in a fingerprint pattern became of interest. Galton made the first attempt to quantify fingerprint individuality. His approach was to divide a fingerprint into small regions such that the ridge detail within each region could be treated as an independent variable. Next, Henry chose an arbitrary probability of 1/4 of the occurrence of each minuta as well as the general pattern type and the core to delta region count. Next, Roxburgh based his model on a polar coordinate system. A configuration of concentric circle spaced one ridge interval apart is taken to represent the ridge flow of the fingerprint. Next, Turing estimated the chance of coincidental fingerprint association in connection with the proposed automatic identification system.